Greetings, dear colleagues. My name is Viktor Stovba, and today I present you results of our work, which is called Using of Ellipsoid Method and Linear Regression with L1 Regularization on Medical Data Investigation. So first we are going to talk about criterion of least moduli powered to P, then discuss the emlmpr algorithm with L1 regularization, and in the end we'll see results of some computational experiments with lambda equals 0 and for medical data investigation when lambda is greater or equal to 0. So we consider linear regression model in form of one. We have m observations, we have n unknown parameters x1, xn to be evaluated, and m is greater than n. The problem 1 can be reformulated as the criterion of least moduli powered to p from 1 to 2, which is a mathematical programming problem, which is a formula 2. If we set here p to 1, we get the least modeling method in the problem 2, and it corresponds to the situation when the errors of our model have Laplace distribution. And if we set parameter p equals to 2, we get least square method in the problem 2, and it corresponds to a normal distribution of errors of the linear regression model. We consider the problem in form of 5. This is the same LP form, but with some additional thing in the end, which is a regularization. It consists of two multipliers. The first one is lambda, which is greater or equal to 0. It is a regularization parameter, and the other multiplier here is the sum of absolute values of elements of vector x. Which is going to balance our model. The algorithm that implements this approach is called emlmpr algorithm. It is based on the ellipsoid method of Shor, and it is presented on this slide. It consists of 5 steps. At the beginning, we set our input parameters, and in the end, we move to the next iteration with values x, r, and matrix b. The computational capabilities of emlmpr are set by the following theorem, and it says that this algorithm can be successfully run on modern computers if n varies from 10 to 30 and m varies from 1 to 10 hundredths. Now let's look at the result of computational experiments if lambda equals 0. The first one shows us the solving time estimation. We have here n equals to 30 and m equals to 300ths. We set matrix A with random numbers on m, and we obtain the vector y set using the matrix A, and x star is also a rand point. And x0 and r0 is the radius where the first point that we start with x0 must lie. The accuracy that we use is f. It's 10 power to minus 6 power to p. So it depends on this value p. And on the bottom of the slide, you can see the results presented in table. The third column shows that we have 5, 6, sometimes 3 seconds to solve this problem with the following parameters. Second example shows us the robustness of LMM method. We have the same example, but here we imitate some outliers here using the following approach. Even components of vector y are multiplied by the value q, which is here. And as you see, the last column of the table shows us the deviation of the solution obtained and the optimal solution that we set here as x star. As you see, if we use p equals to 1, we get the least deviation, which is 1.1 power to minus 10, in comparison with all other solutions. If p is not equal to 1, it's greater. For example, here we have 28, 54, 64, 69, and so on. So it's definitely robust, and the solution times you see here, it's 3 to 2 seconds. Now we move to medical data investigations, and we have 90 patients with 16 features. Actually, when these 90 patients were observed, we obtained more than 200 features, but as a result of feature selection, we save only 16 features, which is the optimal number. These features contain cardiological and basic features, and we prognose back anxiety scale. This thing is going to be predicted. To choose these features among all others, we used sequential feature selector that using R2 quality metric. We use it with scikit-learn version 1.2, and to deal with outliers in some way, we used isolation forest also from scikit-learn 1.2 version, and here we used p equals to 1 and 2. So this slide shows the solving time for the problem, and now we used lambda equals to 0. So as you see, it's 0.56, 0.69, 0.95, and only for one example is 2.15 to solve this problem. The number of iterations are also presented in the column 4 for different values of apps f. This slide shows us model parameters, also with lambda being equal to 0. And as you see, all parameters are quite uniform, but some of them, they are highlighted with in red. They are rather big. It means here that there are some linear dependencies between these factors or features, and that's why we decided to use L1 regularization. So now, as you see, the following slide is the model parameters with lambda equals to 0.1, and this like the same features, they are now highlighted in blue, are rather small, so they are more convenient for this model, and it means that even this small value of lambda is enough to deal with these linear dependencies. So in conclusions, we say that emlmpr algorithm is implemented in Octave, but it's easily implemented in any other convenient programming language such as Python, MATLAB, and so on. It solves linear regression problem with dozens of unknown parameters and hundreds of observations within 3-6 seconds. And also L1 regularization is an effective tool here for finding parameters in linear regression model if its features are linearly dependent, and it allows us to balance the model and obtain normal parameters for this. So we have some acknowledgements here. This work is supported by several grants. It's like Volkswagen Foundation and National Research Foundation of Ukraine, Project of Research Work of Young Scientists, NESU grant for research laboratories, and UTSK and NESU grant as well. Thank you for your attention.